Hello children, please do this problem. Wow, great job. Okay. So we have a slightly spiced lesson today. It goes a little bit beyond the AP curriculum, but just like a tiny little bit, and I'm gonna simplify it anyway. So all we have to do is look at circular motion for the Earth around the Sun. Time to draw a perfect circle. Great job. Okay, so we make a lot of assumptions about the Earth and the Sun when we talk about circular motion. We mostly assume the Earth's going at constant speed, constant radius, perfect circle. But that's not always the case for everything orbiting the Sun. Even though it is pretty much true for the Earth, it's not true for Halley's Comet. I don't know if you guys have heard of Halley's Comet before. It comes near the Earth every about 75 years. It's pretty much cyclical. And people have recorded its passing since way before it was understood, since 240 BC. So how can this be? How can Halley's Comet come toward the Earth and become visible only every 70, 75 years, 80 years? It has a very strange path that's not circular. These are the paths of most of the planets. And Halley's Comet is this ridiculous oval shape over here. So it's only close enough to see every 75 or so years. The rest of the time it's way off in space and we can't see where it went. But it always comes back. And it'll probably come back like 2060, somewhere around there. 2061, I believe, is when it's predicted to be visible again to the Earth. Cool. So, well, why? How can this happen? Let's figure it out. I'm going to erase the Sun and just put a little dot right in the center of the circle. Actually, no, we'll draw the Sun. Not drawn to scale. Okay. So, it's pretty straightforward why the Earth rotates around the Sun at this point, or should be. The Sun has mass m Sun, ms. And the Earth has mass m Earth. I'll call it little m. It's moving with some constant speed around the Earth. But since there's a force of gravity between the Earth and the Sun, there is some acceleration for the Earth toward the Sun. And it is a centripetal acceleration because the Earth's rotation is approximately very, very close to a circle. So we could do a lot of calculations with this, which we'll do later. I'll make a little note of that for myself, so I don't forget. Basically, if FG is FC, GM Sun M over R squared equals MV squared over R. Little m is the mass of the Sun. Mass of the Earth. It's going to cancel out, so we're going to get some nice algebra later. But what if this were not the case? What if the Earth was... This equation assumes that you're going just the right speed. What would happen if you were not the right speed? What would happen to the Earth at its perfectly circular orbit if the Earth was going a little bit faster or a little bit slower? Tell me now. If the Earth were going a little slower, it will eventually spiral into the Sun. If the Earth were going a little faster, it'll spin off and eventually leave the Sun. That's not true. That's a lie. It would be true if the Earth was going much slower or much faster. Yes, if the Earth were to suddenly stop moving or move really slow, the sun's gravity would eventually pull it, and we would all like be pulled into the sun and get burned up and die. If the Earth were going a ridiculous, insane speed, like 1,000 times faster than it is right now, it will, yes, fly off into space and never be seen again. It'll just fly off away from the sun, and we all freeze to death. So that's very sad. But we're going to analyze what will happen if it's just a little bit slower or a little bit faster. And we'll get some interesting ideas. Okay, so let's say, well, right now we just have the perfect formula where the V and R are perfectly matched. The Earth is just the right distance and going just the right speed to have a perfectly circular orbit. Let's keep things simple. What if the Earth were just a tiny, teensy bit closer? Over here. It would still be accelerating toward the Earth, toward the Sun. And it would still have some velocity v. But what would be different? If I just moved the Earth a little bit closer, this then we'll get, it'll be similar to what we said before. If R decreases, V should decrease. But if we decrease R and don't decrease V, we'll get what we were talking about earlier. The sun will start to fly off into space, but it won't fully fly off into space. It'll start flying off into space and end up somewhere over here. Let's say it's over here. Now the Earth is farther from the sun. It still has a tangential velocity, tangent to the sun. And it still accelerates toward the sun with approximately the same acceleration, not quite, but pretty close. Look at these angles. Now, the velocity, what happens? Does my picture look right? Because the speed was a little bit higher, or the radius was a little bit lower, either one would give you the same result. Because V was too high and R was too low, the sun, the Earth, passed the circular orbit. So now it's a little bit past where it was before. It went from too close, now it's too far. It's a little bit farther than it was before in the past. That's fine. That doesn't really affect anything. But look at the way the trajectory is pointed. It's pointed away from the sun. Very, very slightly, just a little bit. But this angle here is a little bit bigger than 90. So the important question for now is, what's going to happen to v, the speed? Normally, the Earth has a constant speed. All things in circular motion, we assume, have constant speed because the acceleration and velocity are perpendicular to each other. But what if they're not? What will happen to the speed? Tell me now. Basically, the velocity, if it's slightly away from the sun, and the acceleration is always directly toward the sun, the velocity, the speed, will decrease. It'll slow down. It is just a tiny amount. It is very small, because most of the velocity is still just perpendicular, tangent to the circle. But there's a little tiny bit that's away. So, it's kind of like the idea we talked about a while ago with like propelling a spaceship with like a fire extinguisher, a very small force. The rocket ship is going at speed v. If I apply a sideways force, I'll have a sideways acceleration. This will not slow down or speed up the rocket ship, it'll just turn it. But if the acceleration is just slightly backward, it'll slow down. If the acceleration was just slightly forward, it'll speed up. So that's what's happening here. Since V and A are not quite perpendicular, there's a little tiny bit extra angle between them. This will slow down the Earth a little tiny bit. So the Earth will slow down as it gets farther and farther from the sun. That's fine. But it'll keep slowing down. So the picture is going to be kind of confusing. Just think about this. The Earth is farther from the sun, but it's always accelerating toward the sun. So, will it keep getting further, or will it eventually stop getting further and maybe even come back? That depends on the speed it's going. But if it was only a little bit off, it will slow down. And over a long time, since it's orbiting around the sun and nothing else is happening to it, it'll slow down, slow down, slow down. It'll eventually reach some point where it's the farthest distance from the sun and it stops getting farther. Now the velocity is perpendicular to the acceleration again. Acceleration is always directly toward the sun. But over here, the velocity is smaller. This whole time that the Earth was getting farther from the sun, it was slowing down. Because as it gets farther from the sun, the acceleration is back toward the sun, and that means the velocity and acceleration are at least somewhat in opposite directions. So this keeps on going, keeps on going. The Earth, it starts out going faster and gets farther. But as it gets farther, it gets slower. So now it's at the farthest, slowest point. And look at the equation again. We have the same formula, mv squared over r. Well, r is larger, and we said that v is smaller. So if we're out far from the sun, but we have a large r and a small v, what will happen? Yeah, what will happen to the Earth? It's a little bit tricky. Remember, this equation is for the perfect circular motion. So I said that this is the slowest possible time. If the v has been decreased, we said, well, if the speed of the Earth is lowered, it'll come back toward the sun. The two rules we talked about earlier were, if it's going too fast, it'll get farther away. If it's going too slow, it'll come back, get closer. So that's what happens. The Earth's velocity, it wouldn't be quite that big yet. It's just a tiny bit toward the sun now. This acceleration is always directly toward the sun, and the velocity, it's mostly tangent, mostly perpendicular, but it just went a little bit toward the sun, just a little bit toward the sun. This angle is now less than 90. So this one is bigger than 90. The Earth is slowing down. This one's less than 90. The Earth is speeding up. So even though it's not the perfect circular motion, you can still get cyclical motion. the cycle is like this. It's not quite perfect circular motion. This equation doesn't quite match up. The Earth is too close to the sun and going too fast. So it gets farther away. But as it gets farther away, it slows down because of the acceleration and velocity vectors we talked about. It shoots off quickly, gets farther away, slows down, slows down, slows down. Now it's very slow and pretty far. But since it's slow, it'll fall back toward the sun. So now it's speeding up, getting closer, speeding up, getting closer, speeding up, getting closer. And if the speed is not too far off the ideal speed for circular motion, it'll continue this cycle. Not circle, cycle, over and over. It'll go from close and fast to far and slow. Close and fast, far and slow. Continuously, over and over. This is the first of 3 laws discovered by some guy. And it's actually true for the Earth and all planets, like Mercury, Venus, Mars. The ones close to the sun, except it's just barely off. Or it's almost perfectly circular. I exaggerated in my drawing. Really, the Earth is only like, if I drew to scale, the Earth would have only been like a millimeter closer and a millimeter farther. And the speed would only change by like another millimeter in the vector. It's very, very small, less than 1% difference. But it's true. This is what really happens in real life, and it's much more prevalent when you look at something like Halley's Comet. All things that orbit the sun have elliptical orbits. They're not perfectly circular, unless you consider an ellipse, or unless you consider a circle an ellipse with eccentricity 0, which you could, that's fine. But they're not technically circular. The whole unit, I was lying to you the whole time, which is very common in physics. It's actually an ellipse. Number 2. This relates to the speed thing I was talking about. Let me erase the vectors. So the solid circle is a circle. The dotted line is an ellipse. Okay, side note, this is not why the seasons happen. This is not like this is summer and this is winter. So this is fall, this is spring. Temperature doesn't depend on the distance between Earth and the sun. It depends on the rotation axis tilt. Earth science, not really physics. Actually, it really is physics, but not important. So we said that over here, the Earth will have the greatest speed. Over here, it'll have the smallest speed. This comes down to a really nice relationship that these ancient, or not ancient, but like medieval astronomers discovered. They took like the set time period, let's say like 30 days, like a month, and they said, well, how far does the Earth go in 30 days? Well, if it's going really fast, it'll obviously go farther in 1 month. If it's going slow, it'll go less distance in a month. Duh. And if it's going medium speed, it'll go a medium distance in a month. That made sense to them, but they phrased it in a very interesting way. You'll never see something like this again. We'll see something kind of related when we talk about angular momentum, but this they called area speed. They said, imagine you draw a line from the Earth to the sun, and then that line sweeps out a distance as the Earth moves. So that's the area in this month over here. In this month, when the Earth is far away and moving slow, it'll make an area like this. And over here, when the Earth's going medium speed, it'll make an area like this. This astronomer who made these observation discoveries, he looked at Mars and Mercury and Venus, and he realized all three areas are the same area, if you have the same period of time for each section. So in 1 month or so, the Earth might go really fast, really close to the sun, or really slow, really far from the sun, but those areas, in theory, are equal. The area is not really important, and no one ever talks about the area speed anymore. So I'll just say, I don't even know, close equals fast, far equals slow. The traditional description is all objects orbiting the sun cover equal areas at equal time or something like that. It's not really important. Simple version, that's all we need to know for now. So cool, there we go. 2 out of 3 laws about astronomy. Rules always come in threes. All right, there's one last rule that was discovered around this time. And we're going to come back to this equation. And even though the first rule is that the orbits are elliptical, to derive the third rule in a simple way, we'll pretend they're circular. We'll go back to circular. And it's fine, because as we said, for the Earth and all the planets, except for Pluto, which is not a planet, so all the planets, bam, it is pretty much circular. The difference between the circle and the actual ellipse is almost nothing. If you saw a picture, you couldn't tell it was not an ellipse, not a circle. So if it is a circle, we can use this assumption. Let me rewrite and cancel out the m, the small mass, the sun. Let me start with the Earth. Gms over r squared equals v squared over r. The nice thing about this is that we cancel the mass of the Earth. So the mass of the Earth doesn't matter. And in fact, this will be true for any object, not just the Earth. It'll be true for Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, also Pluto. It'll be true for all the asteroids in the asteroid belt. It'll be true for all the satellites like Voyager or whatever that get shot up into space and they just drift around the sun observing planets, because the mass of the object cancels out. It doesn't matter that the Jupiter has a huge mass and Mercury is a small one. This started out for the Earth, but if you want to look at Venus, you can use Venus's speed and Venus's radius, and it will still be true, because the equation just says is for any object in circular motion due to gravity. And all the planets and lots of other things will obey this law. So we cancel out the m, we can cancel out r squared with one of the r's. And we're going to make a substitution. Since v is 2 pi, did I mess up? I think it's fine. Since v is 2 pi r over t, the period of rotation, we can square it. V squared is this squared. Capital G, the universal gravitation constant, times the mass of the sun over 4 pi squared equals r cubed over t squared. A very, very powerful equation. But why? This is kind of like a vague question, but what can this be used for? If you're an ancient or medieval astronomer and you look through your telescope, you can see Jupiter, you can see Saturn. You can, I don't know how you would tell, but pretend you can tell how far they are from the sun. You can tell R. What could you predict about Jupiter and Saturn based on this equation? I know it's T, but what does T mean for planets? There's a very nice way to describe it. Tell me right now. All right, so here's the amazing thing. This is true for every planet, and the whole left side is constant for every planet. Let me just quickly make sure I got it right. I did. Physics God, thank you. This is constant for every planet. For every planet, G is the same. It's the same sun, so ms is the same. 4 and pi are constants, so the whole left side is constant. For every planet, r is the distance from the planet to the sun. And r cubed over t squared is constant. T squared is the period of time per cycle, the period of revolution. For a planet, that's the year. That's 1 year. For Earth, it makes 1 full cycle in 1 year. You've probably heard that Mercury is zipping around the sun really fast, and a planet like Neptune is going really slow, barely moving around the sun. You can look it up online. Years for planets. For Mercury, a year is 88 days. For Neptune, it's 60,000 days. But all those values obey this equation. For every planet, the distance to the sun cubed over the year squared is a constant for every planet in the solar system. And amazingly, not just for every planet in the solar system, for every object orbiting every star in the entire universe. If you're looking at a different star like Alpha Centauri or Betelgeuse or whatever, the only thing changing is ms. So if you look at a different star, they were trying to find like a new Earth because we destroyed this one by accident, all you gotta do is plug in a different mass for the star. Instead of the sun, we're orbiting a different star. And then you'll be able to find the year on that planet based on the distance from that planet to the sun. So, really useful tool when analyzing exoplanets. I realize you guys are not doing that very often, but there you guys go. So the third of these 3 equations, 3 laws, are r cubed over t squared is constant. Wow, fascinating physics for a fascinating class during a fascinating year. Okay, there's a little more that I could talk about, but I think that's good for now. Okay, so that's yeah, that's space. That's physics. One last thing. So if this is the sun, and this is something orbiting around the sun, it's actually an ellipse, where you have the fastest speed over here, close to the sun, and the slowest speed out here, farthest from the sun. Let's say this is not the sun, this is the Earth. Well, same thing's true. Everything orbiting the Earth will be fastest when it's closest, and slowest when it's farthest. So here's one last weird thing. in what direction would you want to launch a rocket if you wanted to get off the Earth? If you want to go into deep space, you're saying, I'm done with Earth, it's terrible, let's leave. Which way should you launch your rocket in order to escape the Earth's gravity most easily? Tell me what you think. Most people will say, oh, you want to launch away from the Earth? Just go straight away. That actually, I mean, that makes sense. I don't expect anyone to be able to answer this question, but you don't need to launch your rocket directly away from the Earth. If you launch a rocket sideways with the same speed, it'll eventually also leave the Earth's gravity. Same as the ellipse. In the elliptical path, if you launch sideways, you'll get farther and farther from the Earth, and you'll slow down. But if your initial speed is high enough, you'll be getting farther faster than you're slowing down. I know you can't really compare those things, it's kind of a vague statement, but if you launch off the Earth with some very large speed, the Earth's gravity will slow you down no matter what, whether you're going directly away or at an angle. But it'll be less if you're at an angle. And you can actually use it to like kind of gradually escape the Earth's orbit and fly into space instead of shooting right off into space in a straight line, again, just as far away from Earth as possible. This happens in like Apollo 13, which is real, a real story. This happens in The Martian, I think, kind of. Now this is a very important application. You guys probably know that most rocket launches in the US are done from a place in Florida, like Kennedy Space Center or Cape Canaveral or something like that. It turns out that Florida is the best state in the continental US to launch rockets from. What? What? Huh? What? Huh? Why? Well, you could launch rockets straight up, and in most videos and like movies and whatever, it does seem like the rocket's being launched straight up. But then it usually curves. And you need basically the same speed to escape Earth's gravity no matter what direction you launch the rocket. So why is Florida the best? Well, Florida is the southernmost, is a very southern area. I guess there's also a space station in Houston. That's why there's like Houston, we have a problem. I don't know. I don't know what I'm talking about, but pretend I did. Well, if you launch from a spot on the Earth near the equator, you get some bonus speed because the Earth is rotating too. So if you launch off the equator and go in the direction of the Earth's rotation, your spaceship doesn't start out at rest. It actually starts out moving at the speed of the Earth's orbit. So a very, very small benefit. Well, it's pretty useful if you have to carry like 1,000,000 kilograms of space shuttle into space and then like 2,000,000 kilograms of fuel also. You want every little extra bit you can. So that's why most rocket launches are from southern or equatorial areas of the world. Related, not super commonly asked about the regions, but you do see this equation on the regions sometimes, and these are just simple concepts, so you could see those too. So yeah, it can be more complicated, but these three simple ideas you could see. So we went over them and their physics, and pretty long lesson again, but hopefully I told you guys to like split it up if it's too long, and have a nice day.